Big Testament. Super. All right, good morning, everyone. I hope you can hear me. Um, my name is Mohammad Abedi. This is Physics 2 or Physics 108 class. Um, my email address is mabedi@albany.edu. Our class is going to be on Tuesday and Thursday from 9 to 10:20. The class is going to be held online due to this pandemic situation. The Zoom ID is going to be this. For the university mandate that for each Zoom class we have to have a password. So I set 2591, the last four digits as the password, just a simple way to memorize it. For the office hours, it's going to be right after class. So class usually is going to end around 10:15, and then I'm going to stay on the Zoom for 40, 15 more minutes. So if you have any question, you can come to the office hour. My office is going to be in physics department, room 227. Just in case you want to see me in person, I have other questions. But the office hour is going to be via Zoom. So it's the same as here. For the textbook, so I'm using Cotnell and Johnson physics. We're going to be covering chapter 18 to 28. You don't need to purchase the latest version. I know that the textbook is pretty pricey. I'm using version 7. So any edition that you use after 7 is going to be fine. If you already have a textbook, edition 10, 11, that's perfect. If you don't have it, I highly recommend you to buy one, um, because in the textbook it goes through multiple um, problem sets, and there is a lot of more pictures that's going to help you understand the materials much better. Um, if you don't want to purchase it, at least try to get a PDF version of it. Um, that's I highly recommend to have a PDF version at least. For the homeworks and exams, we're gonna have weekly homework. So after each chapter, you're gonna see homework on Blackboard, and the exam's gonna be on. So the class is not gonna be in person. The exams cannot be in person, so all is gonna be via Blackboard. So both the midterm exam and the final exam is gonna be on Blackboard. Um, the exam's gonna be multiple choice problems, but you're gonna be doing a bunch of calculation to get to the final answer. For the homeworks, they are uploaded to Blackboard, and you have to write down the solution, um, and then upload the solution in PDF to Blackboard. To submit your solution to Blackboard, um, you can handwrite it and then take a picture. If you put the picture in a Word file, then you can save the Word file as PDF. So there are multiple ways to create a PDF. Um, if you have any question about how exactly you can make it, let me know. The easiest way is take a picture, save it in a Word file, just copy it and paste it to a Word file, and then save the Word file as a PDF file. So in the Word file, you can save it as a Word file, or you can convert it to a PDF. And then you have to upload it um, in a PDF form. All right, any questions so far? Can you guys hear me? Just someone say yes, no.
Yes,
Yeah, we
we
can
hear you.
hear
Yeah.
you.
All right, awesome. So this course is going to be about electricity and magnetism. The main idea is that we were trying to answer is that how charged particles move. So what we noticed in physics 1, physics 106, was that we came up with Newtonian mechanics, Newtonian dynamics, where we describe if some object which they have mass, if they move around, how they move around. And we realized that the law for the dynamics was Newton's law, F equals ma. You say that the acceleration of that particle A with the particle with mass m, if there's going to be force on it, then there's going to be acceleration. If there's acceleration, then there's going to be velocity. As the velocity is changing, or the velocity, then the position of that particle is changing too. So basically, that was the kind of the dynamics for objects that have mass. The good thing is that for charged particles like electrons, protons, the particles that they have electric charge, they move according to Newton's law too. Newton's law are dynamics. That's the, we call it classical dynamics. That's the dynamics for the particle. As long as the objects have mass, their dynamics is going to be based on Newtonian mechanics, which is F equals ma. What we are going to see in this book is that for electrical charged particle, the force is going to be between two charged particles. There is going to be electric force. We saw another example in Physics 106. We said that if we have two objects, two masses, mass 1 and mass 2, the force between them is going to be gravitational force, which was g m1 m2 divided by the distance between them squared. So basically what we're going to see is that now if there are two charged particles, there's going to be, for each one of those particles, instead of mass, we're going to have another thing called electric charge, and we use that to find the electric force between the charges. And once you have the force, we plug it to the equation for motion. This is the equation for the motion, F equals ma. And this is Newton's law. Newton's law tells you that if there is an object which has mass m, the acceleration is going to be proportional to the force. But now force could be different. It could be gravitational force. It could be electric force. It could be magnetic force. So there are, or could be friction force. So based on different forces, you're going to have different acceleration. But the whole dynamics, where dynamics meaning there's going to be acceleration, velocity, and position, that dynamic is governed by Newton's law, F equals ma. All right. Any questions so far? So that was kind of the overview of the whole Physics 2 class. All right. So let's start with chapter 18. That's going to be our first lecture. In this chapter, we are going to learn about electric forces and electric fields. So again, the goal for us is going to be, we are going to derive the dynamics for the charged particles, see if there is charged particle objects or charged particles like electrons, how do they move? What we notice in the nature is that the charges, electric charges, they are in two different categories. They're either positive charges or negative charges. The charges, the basics of the charges, or the unit for the charges, is going to be an electron charge, which we denoted by E, which the amount of it, the magnitude is going to be 1.6 times 10 to the power negative 19 with the unit Coulomb. So that's going to be the base units of an electric charge. But we noticed later on, we're going to see that if an object is charged, the number of charge is going to be a multiple of that electric charge, that unit E 1.6, that's going to be a multiple of that charge. For example, if you have an object which is charged, it could have 10 of these electric charges, or if it's an electron negative charge, it's going to be, let's say, negative 100. So it's going to come in a integer units. The unit for the electric charge is called Coulomb. We're going to see that the electric force between two charges is going to be the Coulomb force. He's the guy that came up with that force. If the charges are positive, we usually denote it by positive and if they are negative, you put a negative sign behind the magnitude. For protons, that's one example of the electric charges. Protons are in the nucleus of any atom. Protons are positive charges, and their magnitude of the charge is 1e plus e, which means that the charge is going to be plus 1.6 times 10 to the power negative 19 coulomb. Another example of negative charge is going to be electron. Electrons are negatively charged, and the magnitude for the electron charge is going to be negative 1.6 times 10 to the power negative 19 coulombs. So the thing that I was talking about is that the charges are quantized. This is a new phenomenon for us. For example, when we were talking about the gravitational force between two masses M1 and M2, we didn't say that masses are quantized. We said that the mass could be any number. It could be 10.1256. It could be any continuous number. You can put any digit after the dot. But for the charges, there should be only a multiple of that base charge, that electron charge. So it's going to be some integer number, which could be 1, 2, 3 on of that electron charge. It could not be 1. For example, 2e. That's not going to be a charge of any object. It should be either 1e, 2e, 3e, and onward. So this is a new phenomenon that the charges are quantized. And if you have an object with charges on it, or charged object, the charge of that object is going to be, let's say, 10 electron. It could not be 10 and a half. So that's something new. All right, any questions so far? All right. Please stop me whenever you have a question. If I'm going to be the only person talk here, the class is going to be really boring. So if you have any question, that would be really good for the class. All right. So usually, for those who had a class before with me, usually they know that whenever I introduce any notion, there's going to be an example. Then through that example, I'll illustrate or explain the notion that I just defined. All right, so for the quantized charges, here's an example. How many electrons are there in 1 coulomb of negative charge? So basically the charge Q is going to be 1 coulomb, and we want to see how many electron charges going to be there. Using that equation, Q equals N multiplied by E. If we solve for N, basically divide both sides by E, then E is going to cancel from here, and we have N equals Q divided by E. The charge is going to be 1 coulomb, that's given in the problem. E is a constant, which is 1.6 times 10 to the power negative 19 coulomb. The units cancel out, and we are left with that as a number. So basically, 1 coulomb of charge is 6.25 times 10 to the power 18 number of electrons. So that's 1 coulomb charge is actually a lot of electrons. That's a huge amount of charge. All right, the next is the law of conservation of electric charges. So later on in later chapters, we're going to see electric processes. So electric process is going to be when we have a bunch of charges accumulated in some place and they move around and they move to another object. There's going to be a charge. Zain?
I have a question.
Yes.
For the example that we did, I thought that n was like an integer number generally.
Yes, perfect. So this is actually, this is a integer number. So basically it's going to be 6,
Okay.
2, 5, and then more zeros.
Yeah. Thank you.
Yeah, so it's going to be like 18 zeros, 6, 2, 5, and then now 16 zeros. So that's an integer number. So for the conservation of electric charges, basically we're going to have electric processes where there's going to be charges going to be moving around. And the idea is that the number of electric charges for an isolated system is going to be constant. It's not going to change. For example, if you have a bunch of charges here, let's say 5 electrons here, and over here you have 2 protons. So there's going to be 2 positive charges and 5 negative charges. If those 2 objects are they are connected with a wire such that the charges can move around. So here it was 2e, and here was negative 5e. And before the process, before we connect these 2 objects, there's going to be total of negative 3e. So if you add 2e minus 5e, you're going to get negative 3e. And once they are connected with a wire, electrons going to from here move to the other objects. And once they connect to each other, you're going to have, it's called equilibrium. You're going to see it later on. But basically later on, we're going to, after the process, in total, we're going to have negative 3e. So before we connected those 2 objects, we had negative 3e. One of them was negative 5e. The other one has plus 2e. So total was negative 3e charge. And then after we connect those 2 objects, there's going to be negative 3. So it's not going to be, charge is not going to be annihilated. So basically the electric charges before the process and after the process is going to be the same. So next topic is electric forces. So the question is that if you have 2 charges, how do they exert force on each other? So this is kind of the same as the gravitational force. If you have 2 masses, one of them mass 1, the other object mass m2, if they have 2 objects with masses m1 and m2, what is the gravitational force between them? Here, we're going to talk about the electric force. Basically, if there are 2 objects, they have positive or negative charges, what is the magnitude of the force between them? From the observation, we observe that if their charges are the same, so like charges, the force between them is going to be a repulsive force. So if they are both positive, they're going to push each other away from each other. If the charges are negative again, since they are alike, both of them are negative, the force is going to be away from both of them. But if the charges are unlike charges, one of them is positive, the other one is negative, they're going to attract each other, and that's going to be attractive force between those charges. So it's that comes from observation. As we go on, we're going to see the magnitude of those forces. So that becomes the Coulomb force. We're going to see it in a second. Another thing is that objects that we see in the nature or materials, they can be categorized in 2 different types. First one is conductors and the other one insulators. Conductors are the objects where electric charges like electrons and protons, specifically electrons, they can go through those conductors easily. If an object or material is insulator, electric charges, they cannot go through those materials. They're going to be stationary. If you put the electric charge on somewhere, they're going to stay there. There is semiconductors, which is kind of the in between of those, but actually those are kind of based on some conductors. So that's kind of classification of materials that we see in the nature. All right, now getting back to the electric force, the Coulomb law. So basically, we want to see what is the electric force between 2 point charges. So if you have a charge Q1 and another charge Q2, where the distance between those 2 charges is going to be r, so from center to center, the distance is r, basically the magnitude of the force is going to be given by Coulomb's law. So this is the Coulomb's law. Basically, there's going to be a constant times the charge of the first one, the magnitude of the charge of the first one. These 2 bar is like the absolute value. So if the charge is negative, we have to make them as a positive. And the magnitude of charge 2, multiply them, then divided by the distance between them squared. So this is going to give you the magnitude of the electric force between 2 objects. But about the direction, notice that the forces are vectors. For vectors, basically we should have a magnitude and a direction. Coulomb's law, this formula is going to give you the magnitude of that force. To find the direction, basically we have to look at the signs. If they are both positive, they're going to be both alike, both positive, both or negative. It's going to be a repulsive force between them. If the charges are opposite, one of them is positive, the other one is negative, there's going to be attractive force between them. The K constant is, the magnitude of that constant is 8.99 times 10 to the power 9, where the unit is going to be Newton meter squared divided by Coulomb squared. So that's a constant that we see in Coulomb force. Notice that how similar this is to gravitational force. Gravitational force was a constant, we call it G, mass of the first one times the mass of the second charge divided by the radius squared. These two forces, they look exactly the same. The only difference is that instead of the mass, we have charges. So if it was masses, it becomes the gravitational force between the two objects. And if it's the charges, it's going to be the electric force between them. All right. Any questions so far?
No.
All right. So the next topic is the permittivity of free space. So this the definition for permittivity is that it's a property of free space. If there is a vacuum, no air, free space, there is going to be a constant associated with that medium, with free space or vacuum, epsilon 0. And the formula for it is going to be 1 divided by 4 pi times k, where k is that constant that we defined before. And if you do the calculation, basically epsilon is going to be the permittivity constant, it's going to be 8.85 times 10 to the power negative 12, where the unit is going to be Coulomb squared divided by Newton meter squared. The reason we define permittivity of free space, epsilon 0, is that later on you're going to see more of epsilon 0 instead of k. So these two constants are related using this equation, but later on you're going to see more of that constant. That's actually a very important constant. We're going to see in later chapters, for example, that speed of light has to do with that epsilon. If it's in free space, that's going to be the magnitude. If we are in a medium, let's say that we are in a conductor, that conductor has its own epsilon. So each medium, they have their own epsilon. All right, so now that we define epsilon, the permittivity, then we can go back to the Coulomb's law, and instead of k, we plug in the formula for epsilon. So from here, if we solve for k, k is going to be 1 divided by 4 pi epsilon. Now plugging this k into the Coulomb's law, we're going to have the Coulomb's law in terms of the permittivity constant. 1 divided by 4 pi epsilon, that's going to be the k, q1, q2 divided by the distance between them squared. All right, any question? All right. Again, if you have any question, please stop me. Example, we have 2-point charges. Charge 1 is plus 2 Coulomb, and charge 2 is negative 5 Coulomb. They are separated by a distance of 0.1 meter. Find the direction and magnitude of the electrostatic force that the two charges exert on each other. So we have a charge 1 which is positive, and the second charge is negative. The distance between the charges is 0.1 meter. The magnitude for the charge is given. We can find the magnitude of the electrostatic or the Coulomb force between them. It's going to be K times Q1 times Q2 divided by R squared. K is 8.99 times 10 to the power 9. Q1, the absolute value is going to be 2. The absolute value for the second one should be 5. The absolute value of -5 becomes 5. It should be the positive, the magnitude. Divided by the distance between them squared, the distance is 0.1. Then you have to square it. Doing the calculation, we get 8.99 times 10 to the power 12 Newton. This is really a big force. And the reason is that 1 or 2 coulomb charge is really a lot of charge. We saw that for 1 coulomb, we had 6.25 times 10 to the power 18 number of positive charges. A lot of charges. So this is going to give you the coulomb force, is going to give you the magnitude. To find the direction, so forces are vectors, so we have to find the direction too. Since these two charges are oppositely charged, one of them is positive, the other one is negative, the force between them is going to be attractive. This negative charge is going to exert a force, attractive force on positive charge, so that's this force that I'm drawing right now is due to this negative charge on the charge over here. So it's created or exerted by charge 2 on the positive charge. The other way around, over here, the positive charge is going to exert a attractive electrostatic force on negative charge. So this is on negative charge created or exerted by positive. That's why we see two different forces. The same was true if we had gravitational force between two masses. We see that one of them is created by, and then the other one is going to be on. So that's why we have two forces. The first 2-1 I denoted by 2-1. That's the force exerted by charge 2 on charge 1. So that's the force 2-1. And 1-2 is going to be the other way around. It's created by charge 1 on charge 2. So the force between them is going to be attractive. For this one, F21 is going to be along this direction to the right. F12 is going to be to the left. Now, the thing is that the magnitude of both of these two is going to be the same. They're both 8.99 times 10 to the power 12. The magnitude is the same, but the direction is going to be different. This is basically the third law of Newton. If an object exerts force on the other object, there's going to be exactly the same magnitude of the force on the other object exerted by the first object, but in opposite direction. So these two forces are going to be in opposite direction. That's the Newton's third law. Now that we found the magnitude and kind of we draw the directions, we can write the vector force mathematically in a coordinate system. Coordinate system, in physics 1, we see that we're going to choose a Cartesian coordinate with x and y axis. This is the positive x-axis. This side is the positive y-axis. This side over here is going to be negative x-axis, and the down is going to be negative y-axis. So if we choose the coordinates as such, then the force 2-1 is going to be toward positive x-axis. So F21 is going to be the same magnitude that we found over here from Coulomb's law, now in x direction and in positive x direction. So x hat or I hat, if you have seen those four coordinates, those are the basis units for the coordinate x hat and y hat, where the magnitude of these are going to be 1. All right, so for F12, it's going to be in the opposite of x-axis, so it's going to be in x-axis, but in opposite direction, it's negative direction. So F12 is going to be negative 8.99 times 10 to the power 12 times x hat. So it's going to be in negative direction of x hat. F21 is going to be in positive direction of x hat. So that's mathematically how to write down the force, both the magnitude and the direction. Magnitude and the direction. All right, any questions so far? All right. The thing is that since we are going to be dealing with forces and those are vectors, so we need to know about vectors and trigonometry. Vectors, they have a direction, and if you draw an x and y coordinate, it's going to be the angle, so therefore we need those sine, cosine. If you don't remember them, come to my office hours or try to review your notes for physics 1. All right, so far what we did was the Coulomb's law tells you that if there are 2 point charges, one of them Q1, the other one Q2, and there's a distance between them R, they can find the electric force between these two charges. But what if now we have more charges? Let's say that we have 3 or 4 charges. How do you find the electric force between them? It basically is going to be, you look at those charges 2 by 2. Let's say that I'm looking at all the forces exerted on charge Q over here. What we need to do is that you have to look at them 2 by 2, these two together, find the electric force between them. Then you look at the another 2, and then find the electric force between them. Then you look at the another one, find the electric force between them. And then at the end, you're going to have 3 forces. Some of them could be attractive, some of them could be repulsive force. And then there are 2, 3, or whatever number of charges we have. And these are vectors with magnitude and direction. Then you have to add those forces vectorially, which means that we have 3 vectors A, B, and C. This is each one of them is one of those forces, and we add them as a vector. So that vector addition that we had in physics 1, that's going to come in handy when you want to find the net force exerted by a charge. The first problem is going to be using vector addition to find the net force exerted on a charge. So basically, whenever we have multiple charges and we want to find the force, we can look at 2 by 2 charges, and then there's going to be, for each 2 charges, there's going to be electric force, and then we add all those forces together. For forces, again, are vectors, so we have to add them as a vector. All right, to give you an example, we have 2 charges over here. Charge 1 is 10 microcoulomb, and charge 2 is going to be negative 2 microcoulomb. We are asked to find the net electric force that is exerted on charge Q over here. So we have these 2 charges, the distance here is given, the distance here is given, and we want to see what is the net force exerted on this charge over here. Micro is 10 to the power negative 6. That's one of the units that instead of 10 to the power negative 6, we use micro. All right, so now we have 2 charges, and they exert force on charge Q over here. Notice that this charge Q also exert force on each one of these, but we are now focusing on the charges exerted on charge Q. On this charge, what are the forces exerted on this charge, and find the net force, add them together. All right, let's look at charge 1 and the charge Q that we are interested in. Between charge 1 and charge Q, you see that charge 1 is positive, charge Q is positive, so the force between them is going to be repulsive force. So if the force created or exerted on charge Q by Q1, I'm going to call it F1, it should be a repulsive force because both of them are positive, so it's going to be a repulsive force. Repulsive force means that it's going to push charge Q away. So that's I denoted by F1. If you look at charge 2 now and charge Q, Q is positive, Q2 is negative, so the force between these two is going to be repulsive. Now, if you only focus on charge Q, the attractive, it's going to be attractive force. The attractive force is going to be toward each other. So F2 is going to be toward left, while F1 is toward right. So this is basically based on the magnitude of the charges. If they are positive or negative, we can derive forces, the direction. Now we need to find the magnitude. For F1, that's going to be the force between Q1 and Q. We have the magnitude of each charges. We have the distance between them. The distance is going to be 0.1 meter plus 0.1 meter. So we can find the Coulomb's law to find the magnitude of that F1. To find the magnitude using Coulomb force is going to be K Q1 Q2 Q1 Q divided by the distance between them. I call it R1 squared. K is a constant, 8.99 times 10 to the power 9. Q1 is 10 micro. The absolute value is going to be 10 times the micro. Micro is 10 to the power negative 6. You're going to see this micro a lot for the charges. As I mentioned before, 1 coulomb is really a lot of charges, a lot of electrons or protons. Usually the numbers that make sense is going to be in microcoulombs, much less number of electrons. And the second charge is negative 2 micro. And if you take the absolute value of the charge of the charge Q is actually plus 1. So it's going to be 1 times 1 micro, so 1 times 10 to the power negative 6. So it's going to be between Q1 and Q, between Q1 and Q, 10 micro and 1 micro. The distance between them is going to be the whole distance from here to here. This one is 0.1, this one is 0.12. So add them together, it's going to be 0.2, then square them. Doing the calculation, we get to 2.25 Newton. That's going to be the force between Q1 and Q, and the direction is given. It is to our right. Now, for F2, we can do the same thing. We need to find, we found the direction, we need to find the magnitude. To magnitude, use Coulomb law. Plug in the number for K. Q2 is negative 2 micro. Take the absolute value, becomes positive 2 times micro, 10 to the power negative 6. Charge Q is 1 micro, so it's going to be 1 times 10 to the power negative 6. The distance between Q2 and Q is going to be 0.1. So whenever you use Coulomb's law, that distance should be the distance between these two charges. The distance between these two charges for F2 is going to be 0.1, while the distance between these two charges is going to be 0.2. So that's you have to make sure that whenever you plug in the value for R, that should be the distance between these two charges. Plugging the number, we get 1.8 Newton as the magnitude of F2, which is toward left. Now we found the magnitude of each one of these. We found the direction for each one of these. Now to find the net force, net means add all those forces together that is exerted on charge Q. So basically we have two charges, one to the right and one to the left. And I'm going to choose a coordinate such that the positive x-axis is toward right. Therefore, the net force is going to be F1 minus F2 times x hat, which means that it's going to be toward x-axis. Basically, F1 is going to be, if you write it as, let me write it over here. F1 as a vector is going to be F1, that magnitude that we found, 2.25 times x hat. That's going to be F1. If you write down F2 as a vector, usually as a vector, we write down the name of the force and then we draw an arrow on top of it. F2 is going to be negative F2 times x hat. It's negative because it's toward left. So that's why we have that negative. Now, if you add them together, it's going to be F1 minus F2 times x hat. Basically, you subtract them because they are in opposite direction. F1 was 2.25, F2 was 1.8. Subtract them, you get 0.45 Newton, and the net force is toward positive x-axis. F1 is bigger or larger than F2. Therefore, the net force is going to be toward right, and that's the magnitude. All right, any questions so far?
No.
Yes.
Yeah.
What does the W mean next to 0.45? Can you repeat that? Sorry.
Yes. That is, sorry, you have to deal with my writings. That's actually Newton. That's the unit. So usually, whenever
Okay,
we have,
sorry.
whenever we have any force, let's say force A, we usually write down the magnitude and then the units next to it, and then the direction. So that's the way that we write down any vectors. So there's going to be a magnitude. We usually write down the units in the parentheses, and then the direction. Sometimes instead of x hat, you're going to see I hat. I hat is going to be along x-axis, and j hat is going to be along y-axis. All right. Any other question? All right. So far we discussed about if there are 2-point charges, is that there's going to be electrostatic force between those two charges, and we found the magnitude. Coulomb's law gave you the magnitude of the force between them, which depends on the magnitude of each one of those charges and the distance between them. But we didn't talk about how an object, how these two charges exert force on each other. For example, when we had the kind of that comes from physics 1, basically the kind of forces that you see in nature, some of them we call it contact force, and some of them force at the distance. Basically, let's say that you want to lift a chair. What you have to do, basically, you contact that chair and then lift it. So to exert a force, you have to touch them to exert force. If you want to push a car, you have to touch a car and then push it. You cannot stay far away from a car and push it. That's the kind of, usually we humans, the common forces that we see around us, they are all contact forces. But how do, for example, two masses, two object masses, where there's mass 1 and mass 2, like gravitational force, how do they exert force when they don't touch each other? There's mass 1 here and mass 2 over here. They exert force on each other, gravitational force, but they don't touch each other. They pull each other toward each other, but they don't exert, they don't touch each other. So these at a distance forces, we need a medium to carry the forces. That medium to carry the forces is called field. So what basically field is that it's a medium such that these forces are carried by that medium. In the case of gravitational force, there's going to be gravitational field around each object. The object mass 1 is going to have gravitational field around it, and a mass 2 is going to have its own gravitational field around mass 2. And these two gravitational forces, they're going to contact each other, and because of that, there's going to be a force on each one of these two masses. So that's why we needed field. Now, in the case of electric charges, we have two charges, Q1 and Q2. In order for these two charges to exert forces between them, let's see that the forces are, one of them is positive, the other one is negative, is attractive. In order for these forces to be carried on the other object, there should be a field, and that field we are going to define it as electric field. These charge, each one of them are going to have their own field. Charge Q is going to have its own, that green field around it. That's the electric field produced by Q1, while for Q2 it's going to have its own electric field around it. And these two fields, they overlap. They contact each other, and because of that contact, we are going to see forces between them. So basically, we need to define field just to say how distant objects they exert force on each other. All right. So what we observe is that for each one of those electric charges, so positive charges or negative charges, they have their own electric field. And the thing is that the direction for each one of the electric field, we are going to define it as E. They are going to be depends on the charge. If the charge is positive, at each point, there's going to be electric field, and it's going to be radially outward. So by radially outward means that, let's say that over here, all around that charge is going to be, all the space around it, there's going to be electric field. So even if you go all the way to infinity, very far from the charge, there's going to be electric field produced by that positive or negative charge. Now, we can find the magnitude. So field is going to be a vector, so we can find the magnitude of that electric field to see how strong is that electric field, and we need to find the direction. It's a vector. So let's see that. So basically, all around that positive charge, there's going to be electric field. At each point, there's going to be electric field. That's a field vector. Basically, it means that at each point, there's going to be a vector. So let's say that now getting back to the radially outward, it means that if you're interested to find an electric field at, for example, this point over here, there's going to be a magnitude for that electric field and a direction. The direction is going to be radially outward. So basically, you have to draw kind of this radius between the 2 points, between the point that you are interested to find the electric field and the charge. And then it's going to be direction, it's going to be radially outward. It's going to be along the radius, but it's going to be outward as long as the charge is positive. For example, if you're looking at this point and you want to see what is the electric field produced by charge, that positive charge at this point, to find, we are going to see the equation for the magnitude of electric field. But to find the direction, it's going to be radially outward. So you have to draw a line between the point that you're interested in and the charge, and then it's going to be radially outward. So that's going to be the direction. This one is going to be the direction of the electric field. Notice that at each point there's no charge. What I'm saying that, let's say that there is space, just in the space, at each point in the space, there's going to be field at that point, and it's going to be radially outward. If the charge is negative, again, it's going to be an all around the space around that negative charge. There's going to be electric field produced by that negative charge. And to find the magnitude, there isn't one equation, but to find the direction, it's going to be radially inward. So basically, it means that at each point that you're interested to find the electric field produced by that negative charge, excuse me. So basically, you have to find the distance between them, and then the force, the electric field is going to be radially inward. So this is going to be the electric field. If you're looking at this point, the electric field is going to be radially inward toward the charge. If you look at this point, radially inward toward the charge. If you look at this point, it's going to be radially inward toward the charge. So it's going to give you the direction of the electric field produced by those charges. So again, positive charges radially outward, negative charges radially inward. So that gives you kind of the direction of the electric field. But in order to find the electric field, one way experimentally you can find the magnitude of electric field is by bringing what is called a test charge. So let's say that you have this problem, you have a charge Q, and at some point over here, you want to find the electric field produced by charge Q at this point. What you can do is that to bring another test charge, and it should be a positive charge. We call it Q0, positive Q0. Bring that charge over here, and there is going to be a force between them. Let's assume that this charge is Q is positive. Q0 test charge is always positive. Then there's going to be a repulsive force between the two. We can measure that force. Once you measure that force, then we define, this is the definition, we define the electric force produced by charge Q to be that force divided by Q0. This Q0 is actually the absolute value of Q0. So this is a definition. This is the definition for electric field, how to find the magnitude and also the direction. If you want to find the magnitude, you need to take the absolute value of that equation. Absolute value of E, that's going to be the magnitude of electric field. Absolute value of the force, that's going to be the magnitude of the force, and absolute value of Q0 is going to be the magnitude of the test charge. For the direction, it's going to be the same direction as the force. So if the charge Q is positive, and since the test charge is always positive, that's how we want to carry out the measurement. If this is positive, then there's going to be repulsive force from it, so it's going to be radially outward. That's what we defined over here. Electric field is going to be radially outward. In this case, force is radially outward, so electric field and force are going to be in the same direction. So if I'm going to draw the electric field, let's say that electric field is going to be larger, that's going to be the electric field, while the force is going to be only this part. If this charge Q is negative, the force is going to be along this way, and the electric field is going to be radially inward. So both of the forces and electric field is going to be radially either outward or radially inward. Depends on the charge here. So that's, again, that was the definition for electric field. From this equation, it's a vector equation. We can find the magnitude of electric field and the direction of electric field. The unit for electric field is Newton divided by Coulomb. Newton is the force, and Coulomb is the unit for the charge. Again, since electric fields are vectors, whenever you see a vector, there should be a magnitude and a direction. The magnitude is given by magnitude of F divided by the magnitude of charge Q, and the direction is the same as direction as F. All right, now, if you look at these two charges, one of them is positive Q0, that's our test charge, and the other charge is Q. Basically, because of these two charges given, if we know the distance, we can figure out, based on Coulomb's law, we can find the electrostatic force between them. That force is going to be Q0 divided by the distance between them squared. So R, I'm going to assume that this distance is R. But the force between these two is going to be Coulomb's law, Q0 divided by R squared. Now, if you plug this force into this equation over here, we can find the magnitude of electric field. So it's going to be F divided by Q0. Now, this absolute value of Q0 is going to cancel out. Basically, we have electric field to be K, Q divided by R squared. So that is doing the calculation. This is the electric field produced by charge Q. Notice that there is no test charge anymore. We only use test charge to come up with the equation for electric field. We don't need it any longer. So basically, this equation is telling you that if you have a charge Q, at each point away from that charge with a distance r, there's going to be electric field where the magnitude is going to be that equation. If you go very far from the charge, this r is going to be really large, and if r is really large, the electric field is going to be really small. If you are very close to the charge, if r is really close to 0, very close to the charge, the distance between the charge and the point that you want to find the electric field, if you are very close, if r is really small, the electric field is going to shoot up. It's going to be a really large number. So basically what it means that around that charge Q, around it, there's going to be really a strong electric field. And as you go away from the charge, the electric field is going to diminish. The magnitude is going to become smaller and smaller. Again, the direction for electric field, that was the magnitude. Direction is going to be either radially outward if the charge is positive, and radially inward if the charge is negative. All right, any question? All right, let me give you an example. There is an isolated point charge of Q, which is 15 microcoulomb. A test charge of Q0, which is 0.8 microcoulomb, is located 0.2 meter to the right of charge Q. Find the electric field and electric force produced by Q at the location of the test charge. So basically what we have a charge which is 15 microcoulomb. We have a test charge Q0, which is 0.8 microcoulomb. The distance between them is 0.2 meter, and we are asked to find the force and electric field. Notice that Q is positive. Q0, the test charge, is always positive. So the force between the two is going to be a repulsive force. That's going to be, the red one is going to be the force. The yellow one or the orange one is going to be the electric field. They both are in the same direction. Electric field and the force, they are in the same direction. To find the force, the magnitude is given by Coulomb's law, which is going to be Q0 divided by the distance between them squared. K is 8.99 times 10 to the power 9. Q is 15 micro. 15 micro is 10 to the power negative 6. Q0 is 0.8 micro, so it's going to be 0.8 times 10 to the power negative 6. Distance between them is 0.2. We square them. Doing the calculation, we get 2.7 Newton as the magnitude of that electric force. The direction is toward right. So if you write it in a vectorial form, that force is going to be that magnitude along positive x-axis. So this is positive and along positive x-axis. So that means it's along toward right. So that was the magnitude and the direction for the electric force. The electric force, yeah. Now for the electric field, we use the equation for electric field, which is going to be force divided by Q0 or KQ divided by R squared. We can use both of these equations. We found force at 2.7, so we can use that 2.7 divided by the test charge. That's going to give us 3.4 times 10 to the power 6 Newton per Coulomb as the electric field. Notice that if we do the calculation, if we plug in the value for K, the charge Q, which is 15 micro, and the distance between them is 0.2, you're going to wind up with the same number. So either you can use force divided by test charge, or you use the electric field produced by point charge. That equation is electric field produced by point charge Q. They are going to give you the same number. For the electric field, the direction is going to be toward right. So electric field is going to be that magnitude plus times x hat. So basically, this gives you the direction. All right, any questions so far? All right, I'm going to mention these one more time. So whenever you have a charge, we usually call it point charge. For that charge, it's going to be, let me draw it over here. If you have a charge at each point surrounding that charge, there's going to be electric field. In order for the field to exist, we don't need to have another charge. As long as there is one charge all around the medium, there is going to be electric field produced by that charge. But for electric force, if there is going to be a force, you have to have two charges. You have to have another charge. I'm going to call it Q0. Then we can find the force between the two. But if there is only one charge, there is no force. Force between is always between two charges, two things. As long as there is one, the electric field is gonna exist, but there is no force. So that's a subtle point. You have to make sure that whenever there is a charge, it's going to produce electric field all space around it. To find the magnitude of electric field at each point, you have to use KQ divided by R squared. That's going to give you the magnitude of electric field at each point. Notice that if you are around the charge in some circular point, if you have a circle, the distance from that charge, where the charge is at the center of that circle, there are all some constant number R. We said R is going to be 1 meter, for example. For all these points, the electric field is going to be, the magnitude is going to be the same. So if you look at the equation, magnitude was K magnitude of Q divided by R squared. So at each point on the circumference, if you are interested to find the electric field, the magnitude at each point is going to be the same number. Why? Because K is the same for all of them, it's a constant. Charge is going to be the same because it's the charge that you are trying to find the electric field produced by that charge. And the distance is the same. As long as the distances are the same, at each point, the distance is going to be 1 meter. It's on a circle. So basically, on the circular path, on the circumference, the electric field is going to be the same. If you go to another circle, at each point on that circumference or on that circle, you're going to find another electric field, which is different from the electric field produced on the circle. Between these two electric fields is going to be different, but the magnitude on each point on the front of the circle is going to be the same number. And that's going to be something useful later on. We're going to see it. All right. Any question? All right, I'm going to stop here for today. I'm going to be stay online until 11. If you have any question, please you can stay and ask me. Or if you don't have a question, I'll see you on Thursday.
I have a question.
Yes.
Going back to like on the coordinate system, are the points always going to be on the x-axis?
Good question. So it depends on the drawing. Let's say that I'll give you a system of charges such that one charge is going to be Q1, is going to be, let's say, at the origin, and Q2 is going to be, both of them, let's say for now positive, is on y-axis. For this case, if you want to find the electric field between them, it's going to be repulsive along y-axis. So it depends on where are the location of the charges. So if Q1 and Q2, the distance between them is along y-axis, therefore the force is going to be along positive or negative y-axis. For the same, if I bring another charge over here, let's say Q3, between Q1 and Q3, there's going to be a force. Let's say Q3 is positive 2. Let's make it negative. So if there is a charge Q3 over here, there's going to be another force from charge 1 on charge 3, which is going to be toward negative x-axis. So it basically depends on the location of the two charges that we are interested in. If they're along x-axis, the force is going to be either toward positive x-axis or negative x-axis. If the charges are along y-axis, the force is going to be either toward positive y-axis or negative y-axis. Does that help?
Yes, thank you.
All right, any other question?
Will the Zoom ID and password be the same for every meeting?
Yes, so the Zoom ID is the same and the password is always the last 4 digit, 2591 for my class.
Okay, thank you.
No problem. All right, any other question? All right, so I'm gonna be here online. This is the office hour. If you have any question, you can unmute yourself and ask.